Hello, so today I'm going to tell you about reconstructing genotypes in private genomic databases from genetic risk scores. The long-term privacy of genomic data is a major issue facing genomic databases today. But we don't just need to be concerned about hackers specifically targeting genomic databases and worry about long-term encryption schemes for genomic databases, but rather we need to consider that genomic databases are a dynamic resource. We expect that scientists will continuously propose scientific questions and then use the genomic datasets for generating publications. In and of itself, this only leaks a small amount of information. However, over time, as this resource is used again and again, eventually, this process might release enough information for a hacker to learn something about individuals in the genomic database. What we were interested in investigating was how much we could learn about an individual in the database from the kind of aggregate data that is published. However, we weren't just interested in the type of complementary summary statistics that are sometimes published, because it's always possible to just not include those summary statistics. What we were interested in was the actual scientific output of the research, which scientists have to publish because that's the output of the research project. We were interested in seeing how this could leak information that might be used to identify individuals. We focus on a common research output called genetic risk scores. We start off by performing a genome-wide association study and finding p-values of how different genetic loci are associated with the trait of interest. Then we extract a subset of the significant loci based on a series of heuristics. For example, these SNPs might be far apart from one another, and they might have very low p-values. From this, we would build a linear model to predict phenotype based on these loci. The coefficients of these linear models are the genetic risk scores. Briefly, I wanted to mention the difference between a reconstruction attack and a membership attack. In a membership attack, we ask the question, is this person in the database? In a reconstruction attack, we ask, what is the genotype of a person in the database? In our work, we perform a reconstruction attack. In some ways, reconstruction attacks are even more powerful than membership attacks, because if you know enough information about an individual in the database, then often you can use that to identify a specific individual in the database. The dataset that we use to test our methods is the Cornell Dog Genome Database, which includes over 4,000 dogs and 180,000 genetic loci. The scenario we focus on is as follows. First, we assume that some researchers have used a private genomic dataset to do a GWAS study and generate genetic risk scores. Then they perform the same analysis again, this time adding a subset of dogs. And this generates a new set of genetic risk scores. We also assume that there exists a public data set which we can use to estimate the frequencies of SNPs and the frequencies that pairs of SNPs co-occur in the same individual. We use this information to reconstruct the genotype of the individuals who are added. You might ask, is this a realistic scenario? This scenario is actually very relevant for many real cases. Like here's an example from the UK Biobank. Here, they release the results of two different GWAS studies. In this example, the phenotype under investigation is for people who answered no to the question, do you have hearing difficulty problems? And here, the phenotype is people who answered yes to the question, do you have hearing difficulty? If you look carefully, you can see that there's only one person who responded neither no nor yes to this question. They release information about the carrier frequency, the betas, and the standard error, which is the kind of information which we use to do a reconstruction attack. So it could be that this individual who didn't answer yes or no might have some of his genotype information partially compromised. And you can see that just this one individual has caused a small change in the betas, and this is the information that we exploit in our attack. Here's another example where in this case, the phenotype is heel bone mineral density. And in a second analysis, they look at heel bone mineral density, but they normalize it based on the gender. There's 22 people who are not included in the second study. It's quite likely that these people were excluded because gender information was missing. This could be potentially because they're non-binary or they didn't want to provide the gender. Could the genotypes of these 22 individuals be compromised? We start off with a simpler scenario and then we build up to the final scenario. In the simplest scenario we look at, we imagine that the second study includes one additional individual and that the study releases the exact aggregate statistics. So we know the exact frequency of the SNPs, and we also know the frequency that pairs of SNPs co-occur in the same individual. And what we'll show is that with this information, we can exactly reconstruct the genotype of the individual who was added. The key to this attack is this equation. We calculate this value, D1, based on the genetic risk scores from the original GWAS study, the genetic risk scores after one individual was added, and K, which is the matrix that describes the frequency of SNPs occurring together. The reason this is an interesting metric for us is because this equals the genotype of the individual added, which is represented here as a binary vector, times a scalar. Well, this helps us recover the genotype of the dog with 100% accuracy, because if the SNP is not there, then D1 will take on the value of 0. And if the SNP is there, then D1 will take on the value of C. Now let's expand this case to the case where multiple dogs are added in the follow-up experiment. In this case, instead of calculating D1, we calculate DM, which is very similar to D1 in that it includes the genetic risk scores of the original GWAS, the genetic risk scores after M individuals are added, and also K, which is the frequency table of SNPs co-occurring. Unlike in the other scenario, this vector of genotypes now becomes a matrix of genotypes. And instead of a scalar, we now have a vector of length m. The genotype matrix will look something like this, where each row represents a different SNP, and each column represents a different individual who was added between the two studies. This vector, Cm, might have the values A, B, and C. And if this were the case, then we could see that for every combination of SNPs across the 3 different dogs, you'd get a unique value in DM. You can see this in this example here, where for every possible combination of 3 dogs having a SNP, you'd get a different unique value for DM. Using this, in many cases, we can completely reconstruct the genotypes of all the dogs who were added with 100% accuracy. And in our paper, we provide a specific algorithm for doing so. Next, we expand the scenario to say that we don't know the exact frequency of SNPs or the frequency of SNPs co-occurring in the same individual. In this case, we go back to the scenario where we've only added one individual between the 2 studies. So now D1 is slightly changed in that this K isn't the precise K, but rather is the estimated frequency matrix based on the public data set. So instead of having exactly two different values of D1, we end up with a distribution of values. So in cases where the individual doesn't have the SNP of interest, the mean of this distribution would be 0. And in the case where the individual does have the SNP that was added, the mean of this distribution would be C. However, we don't really know what C is. We also show in our paper that these two distributions should have the same standard deviation. Utilizing this information, we use an expectation maximization algorithm to estimate the parameters of this mixture model, where we estimate C, and we also estimate an additional parameter which describes the variation between K and K hats. Then we can use this to get the posterior and find the probability of each SNP given these D1 hats in our estimated K. We test our expectation maximization algorithm on the Cornell dog database. First, we take a private data set and calculate the genetic risk scores. Then we take a public data set, which does not include any of the same dogs as the private data set, and calculate a frequency matrix. Then we add an additional dog that is not found in either the private data set or the public data set, and calculate a new genetic risk score. And finally, we can use all this information to predict the genotype, compare it with a true genotype, which we know because we were the ones who added the dog. And finally, we can calculate the accuracy, which is the percent of correctly predicted SNPs. We can also compare this to a baseline in which we always predict the most common SNP. We can repeat this procedure with different random splits between the private and public data sets. We find that our expectation maximization works better with larger public databases because this produces better estimates of K. The EM algorithm performs particularly well compared to the baseline when the dog has a higher proportion of rare variants. So here is the proportion of the variants the dog has that are rare, and on the y-axis is the accuracy. And you can see that our method consistently does better than the baseline, and that the gap is particularly wide for dogs that have a higher proportion of rare variants. Finally, we can look at the original scenario we were interested in. For every combination of SNPs that the dogs have, we end up with a different normal distribution of this DM value. In this case, because these distributions are overlapping, we only get a slight improvement over the baseline. But however, remember that we're interested in the long-term privacy of these genomic databases, and that this is only looking at information that's leaked when we repeatedly use the database twice. Over time, if this database were used again and again and again, then there should be enough information to reconstruct the genotypes with even more accuracy. So our final suggestions for researchers who are using genetic risk scores is to be particularly cautious about releasing SNP frequency matrices, even with noise added, because this can improve the reconstruction attack. Also, please don't use a GWAS analysis on the same data, adding just a few individuals, as this could compromise your private information in the databases. I'd like to thank you for listening to this talk, and to thank my co-authors. We represent very diverse research interests.